If you can please take your seats, that would be fantastic. We're about to get started. Plugged in.
Oh, he's right there.
Ready? All right. Well, hi everyone. Welcome back. Welcome back to week 3. Today we'll be talking about Bitcoin mechanics and optimizations. But before we get into that, and before we introduce our guest lecturers for today, we'll get into just an assignment that will be released right after class. So pretty much over the course of the semester, we'll have about 3 discussions. These are just an opportunity to get to do like a deep dive into a blockchain topic of your choice. And so for this first week, or in this first discussion, and you'll have the whole week to do this, it's just like to write a paragraph and do some research based off of a current event. And so it'll all be on B courses, and there'll be more information on there. But the main idea is like you dive into like a current event in blockchain, research it, write about it, and then post it and comment on 2 other responses. And so this is just a way that you'll be able to all learn from each other and kind of stay up to date as to what is going on in the world of blockchain.
Yeah, totally. Also, I know we have a couple new students this week. Hopefully, it's the last time we have to do this. But I'm Ava. This is Nate. We're your course coordinators for this course. The first discussion will be posted tonight. You have, I think, 1 week to complete it. This is basically just because we know a lot of you are super excited about this space, and we want to give you the chance to learn from one another. So take advantage of it, do some cool research, and read about what your peers are learning about as well.
Okay, and if you have any questions, feel free to come and talk to us after class. And if not, yeah, take it away.
Yeah, thank you guys for all coming today. I'm Jaylem. You guys may have seen me from past lectures, and Emma's going to get it started from us. She's so nice to come and give us a guest lecture today.
Yeah, hi, nice to meet you all. So this is just an overview of what we're talking about. First, we're going to be starting with cryptographic hash functions. Okay, so when we're in a trustless environment, we don't want our data to, be out in the open, right? We want to hash it to protect it. So that's why we use these hash functions. Essentially, these are one-to-one mappings of an input of any size to a fixed size output. And it just acts like a regular function, but it has some requirements that we will be going over. So your input will be your message or your transaction. The hash function will hash it for you. Yeah, and then like I said before, the input is of any size and the output will be of a fixed size. And a common hash function is SHA-256, and that is 256 bits. Yeah, so these are essentially the 3 requirements that a hash function must have. So number 1, it has to be computationally efficient, it has to be collision resistant, and it also has to hide any sort of information about the input. So to go into just like a little analogy, I guess if you have an individual and you want to create their fingerprint, then it has to be really easy. The computer should not take a super long amount of time or a lot of computational power to decide on a hash. And then it also has to be collision resistant. So basically, it is a one-to-one mapping. So a different input will always result in a different output. No two inputs should have the same output. And this is not it's never 100% collision resistant because there is a very small probability where you may actually have 2 inputs that can result in the same output, and that actually happened with, I believe, SHA-1, and that's why they moved to SHA-2 and SHA-256, which is a more secure hash function. Yeah, and then lastly, it has to hide information. So given the output, you cannot find out anything about the input. For example, if it's an even or an odd number. Yeah. And then also, a small change in an input should produce a very random output. So you can't find some sort of pattern about the input. And here, like pseudo-random means that one input will always result into the same output. But if you change that input, it will be completely random. So it's not like, oh, you put in the same input one time and like every single time it's different. No, one input will always result in one output. Yeah, and then like I mentioned before, SHA-256 is a pretty popular hash function designed by the NSA, and Bitcoin mostly uses SHA-256 squared, so it applies the function on the input twice, and it uses it for certain things like hashing transactions as well as hashing the block header. Okay, so any questions? Yep. Right, so Jaylem will basically go over this, but the block header is just the identification of a block. It contains the root of the Merkle tree, which is just a data structure that contains all of your transactions. It also has a nonce, which is what the Bitcoin miners are trying to find. And then it also has the previous block hash. So yeah, Jaylem will be going into that in the next section. Yeah, any more questions? No? Okay.
Forgot to announce, these slides are also posted on B courses, so I recommend pulling up the slides so you can follow along and remember any questions that you might have.
Okay, now I'm going to talk a little bit about what the core data structure of blockchain is and what that computation that we talk about when we talk about mining really is. So we say that blockchain is a tamper-evident database because if you make a change to any of the past transactions, it'll appear in the current hashes of the block header. So if we see here, this is all the stuff that's contained in one block. We have a block header, we have a previous block hash, we have a Merkle root, and a nonce. And I'll go one by one and describe what each of these is. So the Merkle root comes from the transactions in a current block. The Merkle tree is the core data structure of blockchain. And what a Merkle tree is every 15 minutes when we have a Bitcoin block, we get all the transactions and we stick them in a tree. And if you guys have taken any CS courses here, I'm sure you've seen trees. And on the bottom, we line up all the transactions next to each other. If there's an odd number of transactions, we'll just go ahead and pad it with additional ones until we get to an even number that can be hashed up into a tree. And what we do at every stage of the tree is we hash together the transactions. So on the bottom, we go ahead and we hash all of them to get the leaf nodes on the tree. We hash each transaction directly, and then we hash together at each level both of the transactions, and then to get to the Merkle root, we hash together the two hashes of the bottom level. So here we see that if you guys are familiar with hash functions, the output will depend entirely on the input, and it'll be pseudo-random. So changing any one of the transactions, any one of the leaves at all, will produce a change in the Merkle root. We can see this here in the next slide. If you tamper with transaction 3, it'll change the hash of transaction 3, it'll change the hash up, and it'll change the Merkle root hash. So in this way, any changes to transactions propagate up the tree. Right here, we can see that in order to prove that a transaction's in the tree, we don't actually need every single transaction in the tree. We only need log n of the number of transactions in the tree. So we can see that to prove that transaction 1 is in the tree, the only other transactions we need are transaction 2, the hash of that, and then we can determine the Merkle root. And this is a useful property because it allows for faster verification as transactions scale up. If it were to scale linearly and not with log n time, it wouldn't be possible to verify the transactions quick enough. Does anyone have any questions at this point about? Okay, so it's a pseudo-random output because given, when you have a hash function, say we give it the letter apple, right? It'll produce something that is completely not related to the word apple, but every time you feed it the word apple, it'll produce the same thing. But say you add an S to the word apples, it won't have a noticeable change in the output where you can say that like, oh, I added an S, so it added this part. It'll completely change the entire output. So just changing one letter or one tiny character will completely randomize the output, but it's still deterministic. So whatever you feed in will get the same output every time. Any more questions?
What did you say happened when there was like a, you said there always has to be an even amount of elements in the tree, right? What happened in the hot case?
You just pad. So basically you just add more transactions and you start pairing those together. Yeah.
So just like the previous slide where I want to verify my transaction one is actually the block. So where I have one B and every Merkle root may be possible, but where I have one B.
Sorry, can I understand the question more? Okay. Yeah.
So by history, I would need B and in order to produce the same Merkle root action.
Exactly.
But then where I have one B, who will give me B and F?
Emma, can you answer that question a little better? Where can you get B and F from?
Right. So, essentially, okay. So basically, his question was, if you have a transaction, how do you get the other transactions that you need to verify that the transaction is in a tree? Right. So, then if you are a miner or someone who has access to the transactions, then you're able to basically have one transaction and then basically find the other one, hash it together, and basically you only need to do log and comparisons, and that's what makes it more efficient. But you do have access to the hashes of the transactions.
Yeah, thank you, Emma. So the idea is that if you're a miner and you're going to be the person doing this proof, you've already carried out the computation on the whole block. So you're going to be storing all of these in like a hash map to support constant lookup time, and you've already performed the computation. So when you're doing the proof, you don't need to perform redundant computation. Yeah, if you're not running a mining node, and you can't do it. You need to be running the mining node, or you need to just go on a block explorer like Etherscan and look for your transaction. But otherwise, you're not storing all the data you need or performing that computation. I think we'll move on to the next section for the sake of time. Okay, so now this is where the idea of the tamper evidence really comes in. We're going to take the previous block header and we're going to feed it into this block. At the very end, to get this block header, what the block header of a block is it's the previous block hash hashed with the Merkle root hashed with this nonce value. And if any transactions are changed in a previous block, we saw in the last slide how it'll propagate up the Merkle root. And because it'll propagate up the Merkle root, it'll change the hash of that block header, and it'll continue to propagate all the way down. I'll show you on the next slide how this is how the previous block hash connects to the next block header. So we can see that if there were to be a change way down the line, it would propagate all the way throughout. Sorry? Oh, the two lines? Oh, that's just indicating that those are all the things we're hashing together. Yeah. No. Oh, sorry. His question was, what do the vertical lines do? And that's just indicating that those are the elements we're hashing together. And sorry, what was your question? Okay, so the block header is a hash. It's the previous block hash hashed with the Merkle root, hashed with the nonce. And if you remember Emma talking about the deterministic hash functions, you can just hash all three together. And then that's why, because it's dependent on those three, that's why when you feed it over as the next previous block hash, any changes would be evident propagating throughout. Can we go to the next slide? So here we show that when the previous block hash changes, it propagates throughout. Any more questions? Awesome. So the last thing we're going to talk about in this section is the nonce value. And when you hear people talking about mining, what they're doing is they're looking for a nonce value that will make the block header lower than a certain difficulty. And mining is really just like wasted computation. It's just spamming a hash function with random inputs, trying to find a block header that will get under a certain difficulty. And if you're the first person in the world that discovers that nonce value for this block, you'll win the block reward. And that's what people are talking about when you win the block reward mining. Bitcoin's proof of work consensus requires you to solve this hash puzzle. And requirements of this hash puzzle are that it's computationally difficult, adjustable, and easily verifiable. We've seen number 3 by the Merkle proof of inclusion. You only need log n nodes instead of n nodes. We know it's adjustable because we can make the difficulty lower. We can just make them get the block headers that they hash to be below a lower number. And over time, we'll see that Bitcoin adjusts the difficulty every 2 weeks or so to make sure that blocks stay mined every 10 minutes, because as more hash power gets on the network, you would think that blocks start getting completed sooner and sooner, but they adjust the difficulty to make sure it takes longer, and it needs to be computationally difficult. And this spamming of finding the nonce value is because if it wasn't computationally difficult, people could just get tons and tons of computers on the network and overpower it and take over by having enough computation power. So Bitcoin's partial pre-image hash puzzle it's a problem. This is the problem I'm describing about finding the nonce. It's the requirement to find a nonce that can be hashed with the Merkle root and hashed with the previous block hash that's less than a target. And that target value is what changes as the difficulty gets harder. So this is Bitcoin's current partial pre-image hash puzzle. The 3 things hashed together need to be less than that address right there. So we can see here that if you hash together the words hello and world, and then you just put in a random value, nonce is just a random number. So here we're just picking a random 0. You'll see that this value is not less than the partial pre-image hash puzzle. So this would be an invalid nonce value, and our miner would move on to picking a new one. We try again with the number 1, and we see once again that the inequality is not true, so we move on once more. And then we finally pick a nonce value that will satisfy the equation, and this is what completing the block is. It's when your mining node that you're running finds that nonce value that when hashed is less than that, and then you found the block and you win the reward and you broadcast it out to the other nodes on the network. Mining is like throwing darts at a target while blindfolded. It's completely random and anyone has an equal chance of hitting it. What differentiates how much money miners will make and how often they'll win a block is how fast their computers are and how quickly they can do this computation, because each time they do the computation, they have an equal likelihood of winning. And yeah, the miners need to make sure to find that hash below the target with the nonce value. Yeah, so difficulty is implemented as you saw with the 0, it was like 0x000f. Well, you just increase the number of leading zeros, and as you increase the number of leading zeros, the problem becomes more difficult. And it adjusts every roughly 2 weeks, which is every 2016 blocks. And as I mentioned, the adjusting is just to make sure that blocks get completed still every 10 minutes as more hash power gets on the network. This example right here is example code of what a mining node is really doing. So we pick a nonce value, and then we just have an infinite loop, and we just go ahead and in this infinite loop, we hash together the things that we're hashing. We hash together our nonce, our Merkle root, and our previous block hash. And then we just keep incrementing the nonce up until we find one that meets the block header. If you want to see a real Bitcoin block, you can go to the bitcoinblockchain.com Explorer. There's also a website called Etherscan for all the transactions and tokens built on top of Ethereum, but for time's sake, we won't look at it here in lecture. Any questions? As we said, they add zeros to the beginning, so it becomes a lower value when you add those zeros. The protocol itself. So that's the thing about Bitcoin. Maybe we'll be able to talk more about like how Bitcoin development works and the management of it works, but basically Bitcoin's maintained by like volunteers, or companies will pay, like have paid, like there's one person that I know here at Berkeley, for example, that's like getting sponsored by a company to work on Bitcoin. So there's one or two people with like access to the Bitcoin core repo, and all these other devs make contributions, but the difficulty of the hash rate is controlled by the protocol itself. So the code itself will make it more difficult. That's part of the beauty of Bitcoin's design. Yeah, you don't actually add a new zero every 2 weeks, but for simplicity's sake, that's the easiest way to describe how it gets harder. Because if you added like a new zero every 2 weeks, you would quickly like run off the map. But the point is that like over time, as it gets harder, over years and years, more and more will become zeros. I mean, along the way, like it increments each digit one at a time, but eventually the idea is that you have more and more leading zeros, and that's like the easiest visual way to describe it. We'll take one more question on this section. Realistically, I haven't looked at like an actual Bitcoin mining script. Maybe they just randomly pick, but it doesn't matter at all because of the nature of a hash function. It's pseudo-random. It doesn't matter at all what number you spit in. There's no deterministic way to see if a lower number or a higher number will have a different effect. It's random, so picking literally a random number and incrementing it by one will work. But in practice, not every miner is going to be starting at zero, incrementing at one. They're going to pick numbers a little more randomly, because if every miner started at zero and incremented their nonce by one at the beginning of a block, like it would be pointless. So in reality, that's just like an example script, but they're going to pick those nonce values randomly. Nate, should we take a few minutes break? Are we okay on time? Okay, yeah, let's take a 5-minute breather here. It's the halfway point in the lecture.
Yeah.
For the hash function, is that unique? So everyone's using the same hash function?
Yes.
So there's only one.
Shot to 56.
Oh, that's a function.
That's a hash function. Yes.
Yeah, thank you.
Oh no. Is that your only question?
Yes, yeah.
Okay, perfect. Thank you.
Oh, what's up?
I'm trying to apply to currently enroll in this course
Oh.
for Berkeley College.
Yeah.
Do you know if I get a signature on it?
I can take a minute to sign it. Do you need, will you do a roll after I sign this, do you think? Or is there anything else that I can help out with, like, on the logistics side? I can totally sign this right now.
I think that this is all you need. I'll have to figure that out after the talk to
Yeah,
advisor about it, but I think, yeah, I'll contact you from it.
I can sign this right now if there's anything to sign. Let's see. Would it be this probably here, right?
Yeah, I'll fill this all out.
Okay, do you want me to sign somewhere?
Yeah, I think it's just like right here. I think that's all.
Here, like,
I had a quick question if you don't mind.
Signing things on my permission.
Without your permission? 15. Yeah, no, feel free to email me if you have any questions about this. We'll go through this. I'll see what I can do. Hey, how's it going? Yeah, so a lot of the few different factors that go into it. One is like how many blocks you have in circulation. So a lot of times that's what we see. And So it's not sort of that, like what was that new block is mine?
I kind of screwed up last lecture, and I didn't take the quiz early enough to get attendance. Is there any, like, do I just have to, like, it's going to be fine? Parker Lishway? Okay, it was like DAI, right? That was the...
I actually don't like look at the
okay. Yeah. Okay, well, thank you.
And so the kind of value that comes from mining comes from when, like the fees that are attached from the device. And so when a person is able to post a transaction, have multiple agreement in the network, and then that block is added. The block is added with just like a bundle integration, but the fees associated from the rewards come from like every transaction. And so what that kind of means is, if I'm going to do Bitcoin, maybe there's like a 1/10 of Bitcoin transaction fee that will go to a peer person who's all that. So that's
And, like,
We're gonna add this to the courses by next week.
Oh, it's not infinite. I'm not sure if they use
yeah, so we're going to talk about wallets next lecture. Have you been here for all the lectures so far?
Yeah.
Okay. So you can think of it's like partially part of the OPTXO model. That's a part of it. We'll talk about wallets next week.
Thank you.
Cool. Should we go back to it? Yeah. Okay, hi everyone. So one quick announcement too. If I can have everyone's attention, please? Okay, we're gonna. That works too. Hi everyone. Just a heads up too, this is a really technical lecture, and I know we have a few students who just joined this week, so try not to be overwhelmed. This will all make a lot more sense with time too, and it's meant to be really challenging. This is one of the trickiest lectures, so don't worry too much about this, and feel free to ask questions, review other lectures, and then we'll be here to help you out all the way. So, let's keep it going.
Okay, now we're going into signatures, the elliptic curve algorithm, as well as Bitcoin addresses, everything that has to do with identity and verifying transactions. So basically, like when you want to send a transaction to another user, you want to maintain two things. One, you want the user to be tied to some kind of identity, but you don't want that identity to reveal anything sensitive about the user, and you don't want that transaction to show anything about the user either. And the solution to that is public key cryptography. So basically this cryptographic system will allow you to create identities for users and use those identities to verify transactions and messages without revealing any of their identities. So in this system, you have a public key. So this is information about a user that you can send to anyone and display publicly. And then you also have a private key. And this is sensitive information about a user, and they should only know about it. They have to be the only person. So in order to generate a public key from a private key, we use something called the elliptic curve digital signature algorithm. We'll go into like the details about this a little bit later, but this algorithm is essentially what Bitcoin uses to generate public keys from private keys. Okay, so how does this actually work? If let's say Alice has a private key. She uses a random number generator to create a private key. However, most random number generators aren't actually purely random. We will go into this a little bit later as well. But she can basically choose her own private key. She then uses the elliptic curve algorithm to calculate a public key. If she wants to send something to Bob, she first has to give Bob her public key. So let's say she wants to send a transaction to Bob. What she wants to do is like, of course, first, she wants to hash the transaction with double SHA-256. And then she wants to create a signature using her private key. And that's created by hashing them, the private key and the transaction together. So she basically wants to send the transaction as well as her signature to Bob. And the signature is used to verify that Alice is actually the one who sent it. If Bob uses Alice's public key as well as her transaction and signature, he can verify that it was in fact Alice who sent the transaction. Let's say there's Eve who comes in the middle. If she wants to take Alice's transaction, let's say she attacked while Alice was sending her transaction to Bob, if she uses her own private key to create a signature and pretend like that message was from her, even if Bob uses Eve's signature with Alice's transaction, like it will basically say that no, this is not like Eve who made the transaction because he has Alice's public key. Yeah, so basically a summary of ECDSA, recipients, when they are given a transaction or a message as well as a signature, they should be able to verify who the message was from, so the original sender, using that original sender's public key. And the original sender can also not be like, oh, no, it wasn't me who sent it. Basically, using their signature as well as their message and public key, the recipient will be able to know that it was the original sender who sent it. And then it can also verify message integrity, so the transaction cannot be modified, basically. Yeah, so any questions so far? Yeah? Okay, so the question was, what is ECDSA used for? Is it just used for person to person? So we use ECDSA to generate a public key from a private key. Like I mentioned before, a private key can be anything you want it to be, but the public key is something that's tied to it but doesn't reveal anything about your private key. So that's what the algorithm does. And using your private key and your public key, you can send someone a message, your public key, as well as a signature, which is using your private key. And then they can use your public key to verify that that message was sent from you using your signature as well as the transaction. Does that make sense? So ECDSA is mostly just used for generating a public key from a private key, but it's helpful if you want to verify transactions because the public key is tied to the private key without actually revealing anything about the private key. Yeah, does that make sense? And then, yeah. Right, so it's a lot more like computationally difficult to crack ECDSA. Yeah, and I guess it's just like a design choice, right? You can also use regular public key cryptography instead of ECDSA, but that's Bitcoin's design choice because it is so hard to crack. Yeah. Any other questions? Yeah. Okay. Yeah, so ECDSA is a little bit different from like a regular hash function. I will be going into that a little bit later. It's like an actual like curve function. And the math that it uses to calculate a private key to a public key is extremely hard to break, but it's not random. Yeah. Oh, yes. Mm-hmm. So that is essentially your private key, right? So you can kind of create your own seed phrase, right, like on MetaMask, and then you can have your Ethereum address be generated. So no, that is the actual private key that you're using. Yeah. Okay, if there are no other questions, I will continue for the sake of time. So this is just a conversion summary. If you start with a private key, you use ECDSA to create a public key, but it's actually a little bit more complicated because the Bitcoin network wants to be a little bit more secure. So they'll basically do double hashing again to create a public key hash. But this time, it's not with two SHA-256 functions, but instead it's with RIPEMD160. This is just for the purpose of not taking up as much memory. It takes up less bits than 256. And then we use another hash function to create the Bitcoin address. Okay, so a little bit more details about private key generation. So private keys are 256-bit unsigned integers. Again, it can come from a seed phrase, but that phrase will be represented by these integers. And they're not generated using regular random number generators. Like if you see like the random function in Python, it's not always actually random, it's actually pseudo-random, and the pseudo-randomness is based on the timestamp, actually. So there are some external libraries that will give you true random numbers, and you can also use a seed phrase, which is basically a bunch of random words together. Yeah, so the chances of two individuals generating the same private key is extremely low since it's 256 bits, so it's around 2 to the power of 256 unique private keys. Okay, and then how do we generate a public key? Using ECDSA. So that's the function that Bitcoin uses. It's a specific ECDSA function. So it's y squared is equal to x squared plus 7 over the finite field of a prime, of a certain prime. So that's just the math of it, but all you need to understand from this lecture is that it's extremely hard to revert back and find the private key from the public key. Okay, and then using the private key as an input, in order to find the public key, there's something called point multiplication that ECDSA does. And you guys, if you're more interested in the math, can go into it a little bit more, but this is not a math class, so you can raise your hand and ask me how it works if you want to know, or come up to me later. But the key thing to note here is it's a trapdoor function, meaning you cannot go back to find the private key. Okay, so yeah, just a summary. The public key, so once you've gotten the public key from ECDSA, you will be using a double hash, so it's SHA-256 and RIPEMD160. Basically, it's 160 bits. At the end, the public key hash is not 256 bits, which takes up less memory and therefore is more efficient for the protocol. And then they use another hashing function to create the Bitcoin address. Okay, any questions? Yeah. Right, so you don't actually want to use a pseudo-random number generator to make your private key because, again, it's not truly random, right? Based on your input, the output will always be the same. That's the case for a pseudo-random function, but you want pure randomness with your private key, so it's extremely secure. And that's why you want to use a random function.
Because it does use pseudo-random, right?
To generate a private key.
Well, just in general, like there's no such thing really as like a truly random function on a computer. Like when we say pseudo-random, the reason it's pseudo-random, that's how all like random numbers are generated on computers. It's because it's based on the number of seconds since Unix time has started, and that's like really the only like, that's like the proper way to set random numbers. I'm not sure if Bitcoin has like a different method, but yeah, pseudo-randomness is just the way computers generate random numbers. And for all intensive purposes, they're purely random. The pseudo part just comes from the fact that it's based on the number of seconds since Unix time started.
Okay, any other questions?
I thought that
Okay, so basically it uses double SHA-256 for most other things, actually everything, including hashing transactions to hashing the block header. But in this case, when you want to go from a public key to a public key hash, we don't use double SHA-256, and we use these two, SHA-256 with RIP-EMD. Yep. Okay. You're welcome. Yeah. Any other questions? Oh, so if we have a public key hash, why are we hashing it again for the address? Well, it's, again, all in favor of security and to prevent the possibility of a collision. Yeah, so if you hash it more times, you will basically, prevent the likelihood of having two Bitcoin addresses be the exact same. Right, so they are deterministic because they are hash functions. So like I said before, an input will always be mapped to one output, right? But there is a pseudo-random nature, right? So no, so a hash function, yeah, you can add on. But basically, your input will be put into the hash function, and the hash function will generate an output that is pseudo-random. Yeah. Do you want to add to that? Yeah, I hope that was clear.
Okay, and now for the last section today, we're going to talk about the Bitcoin script, which is the programming language for Bitcoin itself. A little bit about the Bitcoin script. I don't know if you guys remember from past weeks, but Bitcoin uses a UTXO model. So every time money is spent, the transaction's broken up entirely. And transactions map, thank you, Ava, map inputs to outputs. Transactions also contain the signature of the owner's funds, and spending Bitcoin is just redeeming the outputs of previous transactions and the new UTXOs that were created by them. The script programming language, a few things to note about it is there's no loops in it, so it's not a Turing-complete language like Python, C++, Java. It's not fully functional. It's a scripting language. It's also stacked-based, so if any of you have ever done C and are familiar with memory in C, there's a stack, and this concept of a stack-based language is similar to that in C. And there's also several operators built into the language. A little disclaimer about the language is it's really cool to see and just kind of like learn about it at a high level and to know that it exists and to know what purpose it exists for. But realistically, you'll never be like writing code in Bitcoin scripting language. If you ever do like blockchain development, you'll be writing like Solidity, and Solidity is like the Solidity or another language, but Solidity is the most popular because that's the language for Ethereum, and it's Turing complete. So there's like classes, there's for loops. It's a complete programming language with full functionality, unlike this. So that's why you'll never really be writing script. But if we look at the bottom, these are just two examples of script with script operations, and I'll walk you through in a few slides one specific example of the script programming language. But if you look at the graphic, since it's a stack-based language, you push transactions on and then you pop them off. So scripts in action, the first Bitcoin script was pay to public key, and was brought by Satoshi, which would send directly to someone's public key. And then later we had, these three are the most important. There's other scripts that have now come into place with SegWit, but that's not super important for the sake of this lecture. After pay to public key came pay to public key hash, which then we started hashing the public keys that we're going to be paying to, and it introduced the idea of hash into script public key to hide the full public key in UTXO, because when we had pay to public key, your public key and the UTXO was visible to everyone on the network, but by adding that one layer of hashing, no longer can they see how much is in your UTXO, or they can't see how much money you're sending anymore. And then later we have PSSH, which is pay to script hash, and the receiver became in charge of sending the policy and had to pay for an increased fee size. Something we saw with SegWit is that it took this fees off of the sender, so you no longer have to pay them, but I believe we'll discuss that in a later lecture this year. It's kind of out of the scope of this lecture. It would just take time away from this. I just want to explain this. For P2PKH in action, I'm now going to walk you through the example of the scripting language I was showing you before. So because it's a stack-based language, it's literally we read statements from left to right, pushing them onto the stack. So the code itself is stack-based. So we're going to start by pushing the signature onto the stack. And then the next thing we'll do is we will push the public key onto the stack. And then the next operation we have is called OP_dupe. And what it'll do is it'll duplicate the item that's below it on the stack. So now we'll see that we have two public keys. We have two duplicated public keys, and we've pushed now the next operation on the stack, which is OP#160. And that'll go ahead and perform our hashing for us. So it's RIPE_MD, then SHA-256 on the top item. That's what OP#160 stands for. So it'll perform the hash on the public key, and we will have two PK hashes on the top of the list now, because we had the private key hash. We just performed the OP#160 on the item below, which gave us that public key hash. And then the next item in the stack is also the public key hash that we were given in the code. So we're going to drop it on the stack. And then the next item in the list that we're going to push on the stack is called OP=verify. So now what we're doing is we're checking to make sure that the hash we got from the public key is equal to the hash that we were given in the other part of the code. So now we're going to first verify that the two public key hashes are equivalent. And after we do that, we'll push the operation OP_check_signature onto the stack. And what OP_check_signature will do is it will take the public key and the signature and verify that that's a signature that could validly be generated by the public key. And this is the validation. This is P2PKH, and this is how the validation goes to confirm that that signature and public key can be associated with each other. So the last step is to check that it is valid, and then what we'll see is we get popped onto the stack true, and the script verified our transactions. Right here is the contents of an actual Bitcoin transaction. A few things to note is you can see the script signature, you can see the hash of the previous out, you can see the value of this transaction, and one interesting thing I wanted to point out in the metadata is there's something called a lock time. And the cool thing about lock time is you can give a transaction a certain number of lock time. I believe lock time is measured in blocks. And you could say that I want to make a Bitcoin transaction right now to Emma, but I don't want it to go through the network for 1 year. So let me set a certain number of blocks as lock time, and you can generally estimate how many blocks will convert to actual years, and you can make your transaction not go on the network for whatever the lock time is, or the Bitcoin will just be locked up in this transaction, which there may not be like a huge purpose for, but it's definitely very interesting. Any questions? And now we have time to, that's the last slide, so we have time to take any questions. No questions? Okay.
Don't leave until you do your attendance. That's the next slide.
Oh. The attendance for today's course on B courses is P2PKH. And thank you all for coming out today. Really appreciate it and love hearing everyone's questions, so thanks.
Please don't leave until you do the attendance form. I get like at least 10 emails after class saying, I was there, I promise. I just forgot to do the attendance form, so just takes 1 second. Just do it now.
And then one more thing too, if you ever have any questions or concerns, can you email us instead of sending us a message through B courses? Because sometimes those get jumbled in. So be sure to email us, like the fundamentals email or either of our emails. Any questions about anything there? Yeah. For auditors, yeah, you don't need to do attendance if you're just auditing the class. Okay. Okay. Sweet. Thank you, everyone.